is 0. So the x-intercept is when x is 10.5. So it's going to cut here. There's no y-intercept. So it's not going to cut here at all. Okay? Then what else do we know? At x is equal to 2. Is it 2? 1. We have a positive gradient. So when x is 1 somewhere here, it's an increasing function. If it was a decreasing function, it means at this point it's coming down. So it's going to be going this way. So that's the significance of this. Understand? So it means it's actually going up at this point. So what does that mean? It means it's coming from nowhere. We don't know. We don't care. Then we know it's going to cross this. Something like that. Okay? It says it crossed this. It could have come from here to cross it. It could have happened. Nobody says the function cannot be negative. Of course, a logarithmic function can be negative. If your x is less than 1, you get negative. Understand that? So, you can see already, it could go this way, but the significance of this is to say that, oh, when x is 1, the function was increasing then. So it means, oh, the gradient must be positive here. If you draw a tangent, it's going to go like this. So definitely the curve was like this. If it was negative, then we know that, oh, this is the tangent, right? Then the curve can only come from the top. And since it crosses, of course, it's going to change sign. Does it make sense? So this is all about that question. I found this interesting and I thought, okay, I need to share this with the class. It says show all the features, right? One of the features is that the gradient is 2. So I could draw a tangent here and I just put m is equal to 2. So gradient of this tangent is equal to 2. Okay. And at this point, I have 1. Can you see that? Something like this. Just to show the feature. And the feature here is 10.5 approximately. Okay, label, always label x-axis. You can write y or you can write f of x, your choice. Okay? This is the f of x axis. You can write y-axis and label this as f of x. It doesn't matter. So this graph is the graph of f of x equals that. Any questions? It will never touch base. Make sure it doesn't, no matter how long you draw your curve, it should not touch. Okay? So that's all I want to discuss for curvature, stationary points, now to point of inflection. We have just 7 minutes. If you need anything on the board, otherwise you can pick it later. So I just want to maybe discuss the first few here. So quickly, if you want to copy anything here, or I just explain the point of inflection, then we can even practice this next time. Like I said, we don't have to complete everything, so I don't have to put everything in the test anyway. Let me show you something about point of inflection. We only have a few minutes, so I will rely on this. What's going on, Mr. Epstein? Mr. Chen, can you help? What's your name? There you go. Now, inflection point, or you can say point of inflection. You see, those 2 points are points of inflection. At the point of inflection, second derivative is 0. Because normally there is some kind of example of maximum and minimum that you don't have to go through the sign diagram. So usually what we do to find maximum and minimum sometimes, I will introduce maybe that's a maximum and minimum optimization problem. But you can stick to this so I don't give you too much information for now. But I can show that, someone remind me next time, that maximum and minimum using second derivative. Okay? So come and remind me that. So you can now choose which method you want to go. You want to draw sign diagram, your choice. You want to just apply second derivative technique, your choice. Now, what we do in that method is that, let's say you are given a cubic function. Please do. Let's say you are given that equation. Okay, let's take a random cubic function. Let's take x cubed minus 5x squared minus 2x plus 1. I'm not sure this will work. So you differentiate first, you get 3x squared minus 10x minus 2. Okay? Then you say, oh, at the turning point, first derivative is always 0. Understand? So you equate 3x squared minus 10x minus 2 to be equal to 0. You get x1 maybe a, and you get x2 maybe b. Of course, maybe this is not so easy to do. I'm just explaining something. So you know that you can either get something like this, where this is a and this is b, or you get something like this, where this is a and this is b. So you don't know if a is the point where it is maximum, or if b is the point where it is maximum. So you have 2 cases for a cubic function. That is when your second derivative helps. So then you go ahead to find the second, of course, for every a and b, because we are talking about points, right? So you try to find a f of a, understand? And you try to find b f of b. Do you get the point? Okay, so the points are ready. You just need to label them, to classify them as being maximum or minimum. Then you go for second derivative. That's where your second derivative comes in handy. So for this second derivative, you get 6x minus 10. Then you try to find the sign of the second derivative at this point a and b. So then you say, oh, second derivative at a, you get it. Second derivative at b, you get it. One will be positive, one will be negative. So let's say this is positive and this is negative. This positive tells you, oh, at a you have maximum. The reason we say this is maximum, now you know. If the second derivative is negative, it means the rate at which your gradient is changing is negative, which means your gradient is reducing, which means your gradient was once positive and it decided to change to negative at that point. So you have an upper, a concave down shape. It was positive, then it changed to negative. That's a negative change. Then you classify this. So then you say, oh, if this is 0, minimum. Oh, sorry, maximum. If this is greater than 0, minimum. Something like that. Then you say, oh, therefore, then you now classify them properly. Without sign diagram. This is how I learned in high school. Understand? So we will take 1 or 2 examples on this. Please someone remind me. Then you can compare if you are okay with. But the sign diagram and every other thing, curvature we have done, will help you understand why we are classifying this as maximum and this as minimum. So they all work together. Okay? But the sign diagram also, we expect you to draw the sign diagram and interpret from it. But you can actually just interpret from second derivative also, which is allowed. Understand? So the reason I mentioned that, it's possible sometimes that you differentiate second derivative, you put this stationary point, and you get 0. At the point where you get 0, that is your point of inflection. Because if you get greater than 0, minimum. Less than 0, maximum. But equal to 0, point of inflection. Okay? Now, how do you know if your point of inflection is a stationary point of inflection or non-stationary point of inflection? Put that value of x back into your first derivative. At that value of x, what is the gradient? If the gradient is 0, it means this is what it looks like at the point of inflection. Because the gradient is 0. Then you say this is a stationary point of inflection. A point of inflection with gradient 0. And of course, your gradient is 0 at a stationary point. That's why we call it a stationary point of inflection. This point of inflection is a non-stationary point of inflection. Even though this is where the sign begins again, your second derivative is 0 here. But at the value of x, if you check, it is non-zero when you find your second derivative, but first derivative or the value of x here, it is not 0. So even though it's a point of inflection because the second derivative is 0 at that point, but at that same point, first derivative is not 0, then it is non-stationary point of inflection. You have this summary, so we can go. Somebody remind me, I will re-explain this again, if necessary, next lesson. It's very important. Look at this summary. All turning points may not be stationary points. Because we have some turning points that are points of inflection. All turning points are stationary points, Okay? But not all stationary points are turning points. Do you understand? There are some stationary points that are not turning points. We have just seen that. This stationary point, I'm so sorry. This stationary point is not a turning point. The curve does not turn there. Do you understand that? It doesn't turn because turning is where you have, this is your turning point. Maximum or minimum. Are you getting the point? What? Yeah, this is non-stationary. This is stationary. At stationary, you have dy by dx equal to 0 when you have this. Understand? So quickly, finally, I will explain this again. Look at it. We have some non-stationary points that are, of course, non-stationary points. They cannot intersect. We have some turning points that are also point of inflection. Then they are, everything here is stationary. Everything here is point of inflection. In between are the turning points that are also point of inflection. So they are point of inflection that are called stationary point of inflection. Stationary points are turning points, including some point of inflection. Point of inflection, some are stationary, some are non-stationary. The stationary ones are the ones related to turning points. Okay, so look at this shape. These are turning points. These are non-stationary inflection points. Because at this point, the gradient is still not 0. But look at these ones. The gradient at this point is still 0. The general rule to be a turning point is that your gradient should be 0. So they meet that property. At any stationary point, dy by dx is 0. But the fact that dy by dx is equal to 0 does not mean it is a turning point. Hello? It is stationary, but not necessarily a turning point. Stationary is like saying, oh, I took a break here before I continue my journey. You could have taken a break because you are speeding too much. So you rest a little. Then you continue your speed. Or you take a break because, oh my God, the hill is so high. Let me take a break before coming down. So these are stationary points where you pause a little bit. Am I making sense? Does it make sense? So stationary point is not necessarily turning point. That's the, turning point. Stationary point is not necessarily a turning point. That's the point. This is where you have the turning because you change direction, up, down, down, up. Stationary point is where you pause. Are you waiting because you want to change your direction? Are you just waiting to catch your breath and continue the same direction? So when you change your direction, that's your turning point. When you just continue the same, it's not a turning point, it's just a stationary point. Okay? And point of inflection is where your second derivative is 0. The second derivative could be 0 because of this. Because that is when the shape of the curve changes. Understand? Sorry for taking you. I was even speaking nonsense at the point. I'll show you the demo and every other thing next time. Okay?